The lux is the SI unit of illuminance and luminous emittance, measuring luminous flux per unit area. It is equal to 1 lumen per square meter. In photometry, this is used as a measure of the intensity, as perceived by the human eye, of light that hits or passes through a surface. It is analogous to the radiometric unit watts per square meter, but with the power at each wavelength weighted according to the luminosity function, a standardized model of human visual brightness perception. In English, lux is used in both singular and plural. Explanation: Illuminance is a measure of how much luminous flux is spread over a given area. One can think of luminous flux as a measure of the total amount of visible light present, and the illuminance as a measure of the intensity of illumination on a surface. A given amount of light will illuminate a surface more dimly if it is spread over a larger area. So illuminance is inversely proportional to area when the luminous flux is held constant. 1 lux is equal to 1 lumen per square meter. 1 lux equals 1 lumen per square meter equals 1 candela steradian per square meter. A flux of 1000 lumens, concentrated into an area of 1 square meter, lights up that square meter with an illuminance of 1000 lux. However, the same 1000 lumens, spread out over 10 square meters, produces a dimmer illuminance of only 100 lux. Achieving an illuminance of 500 lux might be possible in a home kitchen with a single fluorescent light fixture with an output of 12,000 lumens. To light a factory floor with dozens of times the area of the kitchen would require dozens of such fixtures. Thus, lighting a larger area to the same level of lux requires a greater number of lumens. As with other SI units, SI prefixes can be used. For example, a kilolux is 1000 lux. Here are some examples of the illuminance provided under various conditions. The illuminance provided by a light source, on a surface perpendicular to the direction to the source, is a measure of the strength of that source as perceived from that location. For instance, a star of apparent magnitude 0 provides 2.08 microlux at the Earth's surface. A barely perceptible magnitude 6 star provides 8 nanolux. The unobscured Sun provides an illumination of up to 100 kilolux on the Earth's surface. The exact value depending on time of year and atmospheric conditions. This direct normal illuminance is related to the solar illuminance constant ESC, equal to 7005128000000000128,000 lux. The illumination provided on a surface by a point source equals the number of lux just described times the cosine of the angle between a ray coming from the source and a normal to the surface. The illumination provided by a light source that covers a large solid angle is proportional to the cosine of the angle between the surface normal in a sort of barycenter of the light source, so long as all of the source is above the plane of the surface. The number of lux falling on the surface equals this cosine times a number that characterizes the source from the point of view in question. Luminous emittance. The lux is also a measure of luminous emittance, the number of lumens given off by a surface per square meter, regardless of how that light is distributed in terms of the directions in which it is emitted. It differs from the luminance, which does depend on the angular distribution of the emission. A perfectly white surface with 1 lux falling on it will emit 1 lux. Relationship between illuminance and a radiance. Like all photometric units, the lux has a corresponding radiometric unit. The difference between any photometric unit and its corresponding radiometric unit is that radiometric units are based on physical power, with all wavelengths being weighted equally, while photometric units take into account the fact that the human eye's image-forming visual system is more sensitive to some wavelengths than others, and accordingly every wavelength is given a different weight. The weighting factor is known as the luminosity function. The lux is 1 lumen per square meter, and the corresponding radiometric unit, which measures a radiance, is the watt per square meter. There is no single conversion factor between lux and W per square meter. There is a different conversion factor for every wavelength, and it is not possible to make a conversion unless one knows the spectral composition of the light. The peak of the luminosity function is at 555 nanometers. The eye's image-forming visual system is more sensitive to light of this wavelength than any other. For monochromatic light of this wavelength, the amount of illuminance for a given amount of irradiance is maximum 683.002 lux per W per square meter. The irradiance needed to make 1 lux at this wavelength is about 1.464 milliwatts per square meter. Other wavelengths of visible light produce fewer lux per watt per meter squared. The luminosity function falls to 0 for wavelengths outside the visible spectrum. For a light source with mixed wavelengths, the number of lumens per watt can be calculated by means of the luminosity function. In order to appear reasonably white, a light source cannot consist solely of the green light to which the eye's image-forming visual photoreceptors are most sensitive, but must include a generous mixture of red and blue wavelengths to which they are much less sensitive. This means that white light sources produce far fewer lumens per watt than the theoretical maximum of 683.002 lumens W. The ratio between the actual number of lumens per watt and the theoretical maximum is expressed as a percentage known as the luminous efficiency. For example, a typical incandescent light bulb has a luminous efficiency of only about 2%. In reality, individual eyes vary slightly in their luminosity functions. However, photometric units are precisely defined and precisely measurable. They are based on an agreed-upon standard luminosity function which is based on measurements of the spectral characteristics of image-forming visual photoreception in many individual human eyes. Use in video camera specifications. Specifications for video cameras such as camcorders and surveillance cameras often include a minimum illuminance level in lux at which the camera will record a satisfactory image. A camera with good low light capability will have a lower lux rating. Still cameras do not use such a specification, since longer exposure times can generally be used to make pictures at very low illuminance levels, as opposed to the case in video cameras where a maximum exposure time is generally set by the frame rate. Non-SI units of illuminance. The corresponding unit in English and American traditional units is the foot candle. 1 foot candle is about 10.764 lux. Since 1 foot candle is the illuminance cast on a surface by a 1 candela source 1 foot away, a lux could be thought of as a meter candle, although this term is discouraged because it does not conform to SI standards for unit names. 1 phot equals 10 kilolux. 1 nox equals 1 millilux. In astronomy, apparent magnitude is a measure of the illuminance of a star on the Earth's atmosphere. A star with apparent magnitude 0 is 2.54 microlux outside the Earth's atmosphere, and 82% of that under clear skies. A magnitude 6 star would be 8.3 nanolux. A standard candle a kilometer away would provide an illuminance of 1 microlux, about the same as a magnitude 1 star. Legacy Unicode symbol. Unicode has a symbol for lux. It is a legacy code to accommodate old code pages in some Asian languages. Use of this code is not recommended. SI photometry units. SI photometry quantities V, T, E. Standards organizations recommend that photometric quantities be denoted with a suffix V, to avoid confusion with radiometric or photon quantities. For example, USA standard letter symbols for illuminating engineering USAS Z7.1-1967, Y10.18-1967. ABC alternative symbols sometimes seen. W for luminous energy, P or F for luminous flux, and Rho or K for luminous efficacy. ABC, J, here is the symbol for the dimension of luminous intensity, not the symbol for the unit joules.